Okay, so thanks all for coming. This is the second talk, the final talk, and then there's beers and food, more food. I'm going to give a talk on how do you actually build a Kafka Streams based microservice architecture on top of Kafka, which is a bit of a mouthful. Before I start, I'd like to get a feel for how many people even know what Kafka Streams is. So if you could all just put your hands up if you know what Kafka Streams is. Okay, that's quite a lot of you. That's good. How many of you have used it? How many of you have built an application with it? Okay, that's a lot less. How many of you have put that in production? That's a lot less again. Okay, that's very interesting. Okay. So the talk, I'm going to give a quick intro of who the heck I am, and then I'm going to talk about a quick overview of the company that this is going to be about. And then this talk is split into two parts. The first part is a kind of a case study where we're going to talk about the challenges and the solutions that we came up against while building a Kafka Streams based microservice architecture. Need to come up with an acronym for that. And then those solutions, we've open sourced them, or we're in the process of open sourcing them. And so the second half of the talk will be a quick demo. And hopefully the demo fairies will be nice. Okay, so who am I? I've lost my notes. I should know who I am, though. I shouldn't need notes. My name's Andy Coates. I'm an engineer of 25 years plus, started in C++, and then predominantly in Java for the last couple of years, or possibly a decade. Last couple of jobs have been work for Apple, where I was part of their big data team, building large-scale Kafka clusters. So I think you mentioned you had one cluster with 5 brokers. Yeah, Apple has gazillion brokers. Their clusters are running kind of like 40, 60, 70, 80 brokers, really pushing the boundaries. So building lots of operations and tooling and UIs around that, and actually helping them build a Kafka as a service offering for the whole of the Apple engineering team. I left Apple to work for Confluent, where I worked on the Streams team, predominantly working on KsqlDb, and I was lucky enough to work on with some really smart people trying to build extensions to the SQL programming language to allow it to express queries into real-time streaming data. So data in motion rather than traditional kind of data at rest in a database. And then I left Confluent when I had an opportunity to go and work for a tech startup, fintech startup, with a couple of colleagues. Neil is here from Confluent. The 3 of us went, and it was an opportunity for us to kind of dog food Kafka Streams and see how it could actually be used. But if I was to sum up who I am or what I do, I'm an engineer. I like building shit, making it work. Okay, so a quick background on the company. It's not that important. We're no longer there, so that's why it's not that important. It was a stealth fintech startup in the market lending platform, building a market lending platform. Does anyone know what margin lending platform? Does anyone know what margin lending is? 2 people? 3. Okay, it's not that important. Okay, basically, it's how the big organizations trade. They don't actually stump up the cash themselves. They ask someone else to lend it to them, and they give them a bit of cash to kind of cover the risk. Okay, so what the platform has to do is build a digital twin to get like a view of all of the customers' positions in the market, so that they can model the risk and work out whether they're holding enough cash to cover that risk. Or give a margin call, exactly. So let's move on to something more interesting. Well, so we'll talk about the challenges we came up against and the solutions. Oh, I've missed a slide. That one. Now, this is an awesome diagram. There will be a test at the end, so pay attention. No, actually, it's a pretty standard, convoluted, complex architecture diagram that no one can read at the back and is not important. But I thought I'd put it up here to show that businesses are complex and therefore architectures are complex. And there's very little you can do about that. You can introduce all kinds of different patterns to simplify your architecture, but ultimately there are lots of connections and there is too much for one person to fit in their head. And this is actually only part of the diagram. This is their risk system. There's other systems. I love the way that someone's taking a photo of this, like they're going to go away and build it later. I'll give you a quick overview if you want. Up here, we have a banking system that allows us to bring in the deposits from our customers so that we know how much money they're holding with us. Down here, we've got a trade capture system that allows us to bring in from lots of different people the trades that our customers are making. And we manage all that information up in the position server over here to build the position that their customers are holding. And we use the market data coming in here to price that. And then we spit it out into some sort of standard financial risk modeling stuff, which spits out some metrics. And we use that to work out whether we're going to put the customer into trade reducing mode, where they can only make trades that reduce their exposure to the market, or whether if the market's really moved against them, whether we ring them up and ask them for more money. And that's basically the architecture. We'll come back to that. But let's first of all talk about the challenges we came up against and the solutions. Where they were. There we go. Thank you. So technology-wise, they had originally built their solution on AWS Kinesis, and they just migrated to Kafka, which is obviously better. And they'd migrated because they had scalability problems with Kinesis. So they were doing that right. And they were building a Kafka Streams based microservice architecture. Really need an acronym. But they had no Kafka knowledge. And so they made all the newbie mistakes that you can imagine. Single topic partitions, no exactly want semantics, which in a financial product is interesting. Timeouts that meant that any time, so default timeouts that meant any time there was a wobble in the cluster, everything fell over. Okay, good. Data formats. They were using primitive keys and JSON values, which is good. No problem with that. But they were manually coding the JSON generation and parsing, which is bad. And they weren't using schemas to validate anything. So they didn't know if their hand-coded JSON that they were writing to their topics was actually valid, which is not a good place to be. And as you can imagine, they had instances where they deployed a new version of a service, and some of the downstream services fell over because the data it relied on was no longer there, and they were getting null pointer exceptions. And finally, the dev process. Oh, hang on, we've jumped again. There we go. Dev process, they had a big mono repo. I don't really want to get into the argument of which is best, whether a mono repo is good or bad, but they had one. Was that sorry? No one cares. Good. I don't care. They had lots of code that was kind of like cut and paste around to do similar things for bringing up and sort of bootstrapping boilerplate code for initializing this service and that service, and each of it was a sort of slightly different version with slightly different bugs. They had very limited unit testing and no functional testing. So at no point did they test this, a microservice as a whole and say, if I poke this in, what do I get out? Manual deployments. And the main thing was, even though all the code was in one repository, it was still really hard to try and extract that somewhat convoluted architectural diagram from the code, because you had to go and like dig around in the service initialization and the service entry point to work out what topics it was consuming and what the config of those topics were and what objects were published to those topics. So we had to improve that, obviously. For the first pass, they'd hired myself and two of my colleagues, so they'd got that right. We fixed the basic stuff. We fixed the low-hanging fruit, so multiple partitions so we can scale. Fix the cluster config and the client config and all that kind of stuff. We introduced Jackson serialization to get between Java objects and JSON, and we introduced the Confluent schema registry with forwards and backwards compatibility to know that we're not going to break anything when we deploy a new version of a service. Oh, by the way, out of interest, who's using JSON here in their Kafka clusters? Hands up, come on, don't be shy. Few? Yeah, okay, how about Pride Buff? Avro? something else. No one's using something. Oh, yeah. Okay, good. And who knows what schema validation is for JSON? Do most people understand what schema validation is? Some people nodding. Good. Okay. How about forwards and backwards compatibility? Do people understand that? Does anyone not understand that? I know you do. You really don't. Ask me at the end. Okay, so, and then over in the dev process, what we started doing is started breaking up the mono repo and pulling out groups of services that together provided business functionality and putting them in their own repo and making that a deployable unit. So rather than having manual deployments from engineers' machines, we had it. So if you change the code, CI/CD would then go away and deploy all the services in that aggregate, that repository. And we introduced, well, we changed the culture so there was more unit testing and there was some functional testing, but that functional testing was generally hand coded. And it would bring up test containers to bring up Docker, and we'd start Kafka and you'd start your service and the schema registry and you'd create topics and register schemas, and it was very verbose and therefore no one really did it. And one other thing we ran into was we were handcrafting our schemas alongside handcrafting our Java classes that represented them. Ultimately, it was slow to develop, so slow. It was slow to develop new microservices because you had to bootstrap all the service initialization code. And if you needed a new repository to put that new service in, it was even slower. We're talking days because multiple people were involved. And it was slow to enhance existing services because there was no functional testing. So if you made a change, did you break anything? You wouldn't know. There had to be a better way. And so we set ourselves, these were the challenges and these are the solutions that we came up with. The first and primary thing we were looking at doing was improving that test coverage. We looked to build in fact, we did build a system test framework that allowed you to write tests in YAML where you define the input that you're going to push into Kafka, and you define the output you're going to expect to get out of Kafka, and you build up test cases into test suites. And this thing just goes away and does everything else for you. It goes away and it will bring up Kafka. It will bring up schema registry. It will create topics. It will publish your schemas. It will create your serializers and all this stuff, so that all you have to do is basically say, I'm going to poke this in, and I might be testing 3 different services working in together, and this is what I expect out. And if I don't, the test fails. That's, sorry? Yeah, if you like. Yeah. And because we wanted to be engineers to actually use this, we wanted you to be able to debug your service inside the Docker container, which is a pain if you have to do it manually. So we implemented it so you could just basically run a plugin, run a command line, put a breakpoint, and it hit breakpoint. And testing's no good unless you can actually capture metrics. So we use JoCoco and hook that up to the Docker container as well, so we can capture code coverage metrics. Now, to be able to do all of this, we needed metadata about the services being tested. We needed to know the Docker containers that they were running, that were being stored in. We needed to know what the input topics were and the output topics were, what the config needed to be, what the key and value type needed to be, so that we could build serializers and we could produce schemas and things. So we created something we call a service descriptor, just a bit of Java code that describes all that. And system tests discover that off the class path and allow it to do its funky stuff, which we'll see in the demo. We realize when we're doing this, we've got this bit of metadata about a service, and we've got code that can use that to create topics, register schema, create serializers. Well, that's what you need to do when you first start up a microservice. So we could actually build a library that would use this to initialize all the stuff, to do all the boilerplate code that was being cut and pasted around the code base, to now in a couple of lines. To speed up the creation of a new aggregate repository where you're going to store some microservices, we created a GitHub template repository. How many people use GitHub, by the way? Good few, yeah. How many people use something else? Okay, get a feel for how many people are just not answering. Yeah. Okay, and we also codified some standard patterns, which we might discuss if I have time. Small thing, we talked about having these handcrafted JSON schemas and the handcrafted Java classes, and the fact that these two wouldn't necessarily align. And so we created some code that would basically build a schema from the Java class, and then we created a Gradle plugin that would allow us to do that as part of the build pipeline. That we won't touch on the demo. And finally, we wanted a way to codify the architecture. So I've been mentioning a couple of times, I mentioned this phrase, the aggregate, which what I mean by that is like a repository that contains multiple services that provide a bit of business functionality. And quite often you see this in like sort of architecture diagrams. You'll get a group of services and someone will put a box around them and give them a name, and that's like an area of business functionality of those services. We wanted to codify that so that it was much easier to look at the code base and understand the dependencies between services and of different sort of functional areas. And so what we did is we sort of extended the idea of this service descriptor to have an aggregate descriptor. And what the aggregate descriptor does is define the public API of this business unit, if you like. And other aggregates are not allowed to talk to any of the topics or consume any of the topics that are used internally in that aggregate. They can only use the topics which are public from the aggregate. And those topics will contain sort of data sets that team or that business function have deemed as being consumable by other people. Okay, so we'll go back to the lovely architectural diagram. Just to kind of help people understand what I mean by aggregates in case it's I'm not explaining it very well. I said before, we've kind of got this banking gateway stuff up here. And what people would do in an architectural diagram is they'll say, oh, that's the banking business function, or for Creek, that's the banking aggregate. Down here, we've got market data and trade capture. Across the top, we've got some reference data about our customers and our instruments. All that in the middle is the position server, which is calculating risk. And then from those, we monitor the risk, and then we act on the risk, or we mitigate the risk. This isn't something new. I'm not saying that I've invented this. This is quite a standard pattern, but I'm just trying to explain what I mean by these aggregates. And of course, this is only part of the system. And so when you start zooming out, you have another layer and say, well, all those things in there, that's just the risk system. And so you can have this concept of you can have an aggregate of aggregates. And again, you have a public API that you expose to the rest of the business, and people are only allowed to consume that public API. And so we start breaking the system down into sort of higher and higher level abstractions that people can get in their heads. And if you're working in one area, you don't care about the complexities of the rest of the area. You only care about the public API of that area. It just makes it easier for people to mentally process and build up that really important mental picture of what's going on in the system. And then inside an aggregate, this is one of the aggregates off the diagram. You can see here we've got two Kafka Streams microservices, one with a state store and some internal topics, but none of those are accessible outside the aggregate. It's consuming the public API of the position and the party aggregate, and it's producing a topic down here, which is its public API or part of its public API. Okay, so time for a demo. Just quickly, the demo will cover the following. Step one, we're going to bootstrap a repository, create a new repository to store some microservices. We're going to add a Kafka Streams microservice module to it. We're going to define the services metadata. So we're going to create that service descriptor I talked about and define some input and output topics. We are going to write the business logic, which is not important, but we'll need some, because then we're going to write some functional tests, system tests in YAML. And then because it's cool, we're going to put a breakpoint in the code and hit it And we're going to capture some code cover metrics. And I'm now going to try and get the demo working. So pray. I've lost Zoom. Where's my Zoom window gone? Uh-oh. Bring all windows to front. Why did Zoom do this? Why does it lose windows? I have. Yeah. Ah, here we go. Got it. Got it. Well done. Thank you. Okay. Oh, it's the wrong window. Oh no. I'm actually going to go back to the window I was on. So okay, so this is the aggregate template. It is a template repository in GitHub. This is how you create a new repository to store your microservices in. The idea is that you wouldn't necessarily use this one every day in your organization. The idea is that you would use this to build your own template with your own kind of ways of doing things. This gives you like a starting point, but I won't actually run the entire thing. But to create a new repository, it is really as simple as giving it a name. And clicking a button. And GitHub will hopefully create a copy of the code. Nothing new there, nothing exciting there. But then what happens is there's actually a script which we've written, which runs in the background. And what that does is it bootstraps the repository. So it takes the owner and the sort of the repository name and customize the code. So all of your packages, all of your artifact names and things are all customized to match the naming. This takes a couple of minutes to run, so I'm not going to stand here and make you wait. We'll just quickly have a look at how you would add a microservice. So we have a workflow for adding a new microservice. So we could call this Bob, and you run that workflow, and it will actually create you a service called Bob in this new aggregate. But we're not going to run that because it takes too long. And by too long, I mean more than 2 minutes. So instead, we're going to switch to one I prepared earlier. Excellent. Now I need my notes. Okay. So this is pretty much as the template repository would create it. And I've added a service called handler current service, because what this demo is going to do, bit of a noddy example, all it's basically going to do is going to consume a stream of tweets, a topic of tweets. It's going to look for occurrences of tweet handles, you know, the @Elon Musk, and then it's going to output those counts to another topic. So very noddy, but it's not. It's more about showing how Greek can help you write that really quickly and test it, rather than the actual business functionality itself. So the first thing we're going to do is we are going to create the service descriptor. So this is the bit of metadata that is used by the service initialization code and by the system tests to do its thing. So in our services module, the workflow has already created us an empty one, a basic one. And you can see down here, maybe at the back, is it's already set the Docker image name. That's already populated. And all we're going to do is I'm going to paste in some code, which hopefully people can read. Ish. If you can't read at the back, you'll have to move forward. So basically what it's defining is an input topic and an output topic. And we define the topic name, and we define the key type and the value type and the config. So this has got 5 partitions, this one's got 6 and a retention time. And that's pretty much customizable by you, sort of what config you want to set. Now in this actual example, to keep things self-contained, the input topic and the output topic are both owned. And by owned, I mean they are the responsibility of the service itself. and therefore the team that owns that service. It's more common for services to own their output topics, not generally their input. They're normally consuming upstream topics from other services. And if that was the case, this would be an unowned input topic. There are tutorials on the website that show how to do that, how to kind of import data from other services or aggregates. So the next thing we're going to do is create a load of business logic. Oh, just briefly before I do that, this is the entry point for the microservice. So rather than having loads of code in here that's really complex, this is the service descriptor that we've just created that says what the service's inputs and outputs are. You pass it to this library, and it does all of the bootstrapping of the service for you. And then you just get hold of the streams extension and pass it to the topology builder that we're about to build. That builds the topology, and then we just execute that using our streams extension. Okay. So scroll up. Can't quite get all of it on the screen at once, but okay. So at the top here, we've got a standard Kafka Streams builder. And then these constants were the constants we defined in the service descriptor. And we're just passing those to Creek and saying, give me back a type safe object, which allows us to access the metadata about that topic and things like the serializers. We're then just creating an input stream where we're consuming our input topic and we're passing in our key survey and our value survey, and we've named it. And bad things happen if you don't. We're calling a bit of business functionality, which we're calling extract handles, which will return 0 or more handles that are detected in the tweet. And then we're outputting that to a new topic. And this is a very basic Streams app using the DSL. The details are not that important, but for those that are interested, the extract handles looks a bit like this. All it's basically doing is searching the tweet text using a regex. And that's it. We've now just built a microservice. And when I say we've built a microservice, if I was to run, for a mic. Thank you. Assuming I've felt that right. This should then, hopefully, go away and build the Docker image. And if you were to commit this code to the repository, it published the Docker image to the GitHub repository. So you could then go away and deploy it. So I hope you appreciate or see that was quite quick. Fairly noddy service, but a lot quicker than what it would do by hand. So let's get onto some system testing. Well, it's not production ready because no one's written any tests yet.
I think the talk is more about Confluent testing.
I really could do with a third hand. Okay, sorry about that. I need 3 hands. So all I've done here is I've created a YAML file in the inputs directory, and I've given it a name. The name's not important. And the contents of the YAML file is basically, it's saying that the file contains messages that are going to get put onto a Kafka topic. It gives the name of the topic, and then in this case, we've only given a single input record that's going to be produced to Kafka. The test framework supports actually sending in seed data, which is data which is fed into Kafka before your services start. This is actually sending in an input, which is sent into the system after your service is started up. I'm now going to add a expectation where I have to put down the mic again. Okay. So this is very similar format. This is the expectation. This is what do we expect to come out from the service? So again, we're saying it's a Kafka topic. This is the topic name, and we're expecting these records to come out. And the final thing we need to do is to create the test suite itself. Okay, I'm hoping people can read that. So this is just a test suite. You list the services that you want to start, and that can be multiple services. They're started in the order they appear. The system test will then go away and inspect those services and work out what third-party services need to be started. Do you need to start Kafka? Do you need to start a schema registry? In the fintech startup, we had it also starting Postgres databases and initializing them and initializing AWS buckets, all kinds of different things. At the moment, the open source project just supports, is focused around Kafka Streams. And then we've defined a single test case, and all we literally do is say, these are my inputs. I want to send in this input file, and my expectations is that output file. And you can send in plenty of different inputs, and have lots of different outputs, lots of different test cases. And that's it. We've written a test case. Okay, so all I'm going to do now is just run the system test from the Gradle plugin, which is quite small. And you can see, if those that are at the front, they can see Kafka starting up and the handle occurrence service starting up. And then it all kind of sort of shuts back down again, which isn't that exciting as a demo, sort of running it. But what I want to show is also that you can set a breakpoint. So let's put a breakpoint in the extract handles method. I need to run a little plugin called Attach Me. I don't know if anyone's aware of this plugin. It's actually by JetBrains, the authors of IntelliJ. It's a really useful little plugin. It basically makes IntelliJ listen for incoming connections to the debugger as opposed to outgoing connections only. So we run that, and then slightly different command to run. So for those that can't read that at the back, basically I'm invoking the Gradle build with system test command, and I'm telling it the service I need to debug, which is the handle occurrence service. And I've increased the verification timeout just so that we can actually hit the breakpoint and it not disappear. And if the fairies are nice, there we go. Thank you. So let's get rid of that. And as I said I would do it, I will bring up the coverage. So it's just using JCocoa, but it's you have to kind of load the JCocoa agent jar into a mount point that you attach to the Docker container, and you have another another mount point where the results can be written, and you have to do some kind of voodoo to make it all work, which you can all it's easy enough for you all to do. It just takes time. So that's now finished. And so down here, go away. There we go. Again, in very small text. Huh. The fairies are not nice. That should be much higher. Okay, so something's gone wrong, which I'm unaware of, but normally this would be very close to 100% code coverage. Not certain what the cause of that is, but trust me, it does actually work. Okay, so that's the kind of the demo complete. Let me come back. Yeah, there we go. Okay, so just in summary, come on, wrong window. Sorry, folks. That one? Yes. In summary, the main thing we were focusing on was improving test coverage and effectiveness. And with the system tests in place, what we actually saw was the functional testing went from basically non-existent to basically everyone doing functional testing and getting a good level of coverage from that. We wanted to make it possible to really easily debug the code so that you're not having to rely on printfs and log lines to be able to work out what's going on. This introduction of the codifying of the aggregate APIs, these putting the architectural boundaries into code, meant that it was really easy for teams or developers to collaborate. And in fact, often they didn't even need to collaborate because the public API was already defined and therefore they could just go and consume it. And there's nothing engineers like more than not talking to other people. We tried to make Creek opinionated in that it tries to bring good practice, because Kafka is really open. You can pretty much do whatever you want to it. So Creek is deliberately opinionated. It has a way of doing things, but it's designed so that it makes it easy to do the right thing, hard to do the wrong thing, but it doesn't try and hide the technology from you. So it's all there. You can customize most of the code that's in the template repository. And it's not trying to abstract away Kafka Streams. It's just trying to make it easier to use Kafka Streams. It's built from the ground up to be extendable. So at the moment, it's focused on Kafka Streams. We're working on a JSON serializer at the moment, and we're going to look at Avro, Protobuf, whatever. But it's actually designed to go beyond Kafka Streams. As I said, in the startup, we had it talking to Postgres databases, cloud services, REST endpoints. And the idea is that we'll extend it to do that as well. And best of all, it's free. And so hopefully, if you are using microservices and Kafka Streams, microservices, you should hopefully start using Creek. Just very briefly, how's time doing? Roadmap, as I said, we're building JSON schema validated serializers at the moment. So at the moment, it's just primitive keys, but that's going to change very soon. We've got some work to do on state stores. And once that's done, it's kind of ready for general adoption with some future work around system testing improvements and codifying some of the sort of really cool patterns we developed while at this tech startup. And that is pretty much it. So then we go down to questions.
Does it work with Confluent or also with
It's just a client library, so it works with anything. Oh, it's just a client library. So it's working, it's a library that sits beside Kafka Streams library, client library. So it'll work with Apache Kafka, it'll work with Confluent Cloud, it'll work with AWS Kafka or whatever you want. It'll probably actually work with, is it Red Panda, the C++ one? There's no reason why it shouldn't. What was that, Tony? Anyone else? Yep. Yep. Okay, so the question was, in terms of defining an API for an aggregate, what enforces that API? So the API is, in the startup, was predominantly Kafka topics. And so what the aggregate descriptor is packaged in a jar that other services can pull down and start to consume. And it has the definitions of the topics that form part of the public API. But it could be other resources. It doesn't have to necessarily just be Kafka. And they can, so rather than having to sort of redefine the types of that topic, so the topic name and the key and value types, it's all in that jar. And you can just reference it in your service descriptor. And then in the Kafka side, we haven't built this yet, that's coming later. There will be ACL provisioning. That means that only users that have access to the public topics will be available to everyone, but the internal topics will be restricted to the service accounts that those services are running. Does that answer your question? Yes. Yep. There was another question at the back somewhere. Sort of. Yep. So the question was kind of around secret management and how do you empower the engineering teams to be able to define the config in the code, you mean? So in the tech startup, we actually initially didn't have ACLs. And so it was, engineers were trusted to do whatever they wanted. So they defined the config and the services on startup actually provisioned their own topics. And they're running in accounts that have permissions to do that. We did introduce ACLs, or we're in the process of introducing ACLs along the way. And with Creek, we do plan to do that so that it will provision ACLs on the cluster to control access to the resources. In terms of managing the secrets around that, it's very much organization specific. So we can provide some advice and some patterns that you can use, that sort of ways of customizing the aggregate template to allow you to facilitate that, but it's too specific. Oh, you mean at the startup? Yes, we were using AWS Secret Manager, which then, thank you, Neil, the secrets got injected into an environment variable that the service then picks up on startup. And Creek supports that, so you can define the endpoints for your cluster and the credentials that you use to connect to that cluster all get read from an environment variable. So if you're running in a cloud service, you can just use something like Secrets Manager to create that. And then it all starts up with the right credentials. Anything else? Yeah. Sort of give me an example and I'll be able to answer whether it will support it. Yep. So in the startup, the implementation we had in the startup was more advanced than what we have in Creek right now. And by default, what it would do is whatever you define in the output expectations file was exactly what it wanted in the topic, right? So if you expect 5 entries, you put 5 entries there, and it would fail if there was 6, which is kind of, if your join is producing too many records, you detect that. But you could also change the mode in which it was doing the comparison and just saying, I expect at least 5 messages, if you want to be a bit more lenient. And the expectation also didn't have to provide all the fields. You can just actually say, I expect the object can have many different fields, but this one needs to be set to this value, and this one needs to be set to this value. So you can kind of have this partial matching. Does that kind of meet? Yep, good. You've already asked one. Anyone else first? Okay, you can ask yours. So at the moment, you'd have to go and look at the code, but there is plans to have tooling that would basically inspect all of the aggregate and service descriptors and use that to build an architectural model for you. Yep. Yep. Okay, yeah. So the question was, if you're using the GitHub template repository to bootstrap your repositories, then what happens when Creek updates and how do you update everything? I would basically suggest Dependabot. Are you familiar with this? Because Creek's just a jar. or several jars. So you would update it anyway that you would normally do that. So you can configure your GitHub repositories with Dependabot, and it will go away. And every time a new version of Creek's released, it will open a PR for you and say, hey, new version. You know, once we are at maybe not GA, probably GA, we're going to start focusing more on backwards compatibility on the API. And the jars themselves are very clear about, they're all using Java 9's module system. Yeah, okay. And clearly defining what's public API and what's internal and things. So the backwards compatibility picture for the jars should be quite easy to maintain. Cool. Thank you very much, people. You can come and see me afterwards.